For as long as humans have looked up, we've carried one quiet certainty: that someday, with enough time and cleverness, we'll leave Earth behind and sail to another star the way we once crossed oceans. Every generation that's dreamed it has believed the same thing, that the distances are vast, yes, but that technology always catches up, that if we can split atoms and land on the moon, then reaching Alpha Centauri is only a matter of patience. But there's a possibility almost no one speaks out loud, that the universe itself may have built a wall we were never meant to cross, a barrier woven not from engineering limits, but from the fabric of physics itself. This film names that wall. Before we can see the wall, we have to understand the promise it quietly cancels. The promise. The dream of interstellar travel didn't start with rockets. Ancient Greek philosophers imagined countless worlds scattered through the void. In 1584, Giordano Bruno proposed that stars were distant suns, each with their own planets, their own civilizations. By the 20th century, the dream had blueprints. Konstantin Tsiolkovsky sketched multi-stage rockets in 1903. Robert Goddard launched liquid-fueled prototypes in 1926. Then we built Saturn V, crossed 384,400 kilometers to the Moon, and sent Voyager past the edge of the solar system. Every mission felt like proof that the next leap was inevitable. We'd gone from wooden ships to orbit in 500 years, so surely the stars were just another ocean, just another decade or two of breakthroughs away. But the moment you measure the neighborhood, the dream starts to look very different. A sky full of suns. Our galaxy holds somewhere between 100 billion and 400 billion stars. At least 100 billion planets orbit those stars, maybe twice that number. A third of sun-like stars host rocky worlds in the habitable zone where liquid water can pool. In 2009, the Kepler Space Telescope stared at a single patch of sky no bigger than your fist held at arm's length. In that tiny sliver, it found 2,662 planets, around 2,000 stars. Scale that up, and the Milky Way becomes an ocean of destinations, worlds with mountains, storms, maybe even forests or ruins. The James Webb Space Telescope has photographed galaxies formed just 300 million years after the Big Bang, each one carrying billions more stars. The cosmos isn't empty, it's crowded beyond comprehension, glittering with possibility. Therefore, the real question was never how many stars there are, but how far the closest one hides. The nearest light, that closest star, has a name: Proxima Centauri, a red dwarf barely visible to any telescope, locked in orbit around the binary pair Alpha Centauri A and B. It sits 4.24 light-years away. Light-years flatten distance into something that sounds manageable, like kilometers or miles stretched a little further. But a light-year is 9.46 trillion kilometers. Proxima Centauri is 40.1 trillion kilometers from Earth. To cross that gap, you'd pass the orbit of Neptune 4,760 times. You'd fly the distance from Earth to the Moon 104 million times over. The number stops meaning anything to human intuition somewhere around the second trillion. Put a real spacecraft against that number, and the arithmetic turns cruel. Voyager's crawl. Voyager 1 launched in 1977, slingshot past Jupiter and Saturn, and has been coasting ever since. It's the fastest object humanity has ever sent beyond the solar system, moving at 61,000 kilometers per hour relative to the Sun. It crossed into interstellar space in 2012. At that speed, Voyager 1 would take 73,000 years to reach Proxima Centauri. Not 73 years, 73,000. That's longer than modern humans have existed as a species. New Horizons, which flew past Pluto in 2015, moves slightly faster, at 58,500 kilometers per hour on its outbound trajectory. It would still take 78,000 years. The Parker Solar Probe touched 163 kilometers per second near the Sun in 2021, but that was a gravity-assisted dive, not a sustainable cruise speed toward another star. The obvious fix, just go faster, is exactly where physics sets its first trap. Reading the distance. Those 4.24 light-years aren't a guess. Astronomers measure stellar distances using parallax, the same trick your eyes use to judge depth. As Earth orbits the Sun, nearby stars appear to shift position against the distant background. The smaller the shift, the farther the star. Proxima Centauri shifts by 0.7687 arcseconds over 6 months. That's 1/4685th of a degree, measured to within a fraction of a percent by the Gaia Space Telescope. The trigonometry is high school level. The distance follows directly. For stars beyond a few hundred light-years, parallax gets too small to measure. So astronomers use standard candles, stars whose intrinsic brightness is known. Cepheid variables pulse at rates tied to their luminosity. Type 1a supernovae explode with nearly identical peak brightness. Compare apparent brightness to true brightness, and the distance falls out. With the distance locked in, everything now depends on the machine, so we go looking for one. The dream machine. The 20th century gave us a catalogue. Von Braun sketched nuclear pulse ships in the 1950s. Freeman Dyson's team at General Atomic ran the math on bomb-powered acceleration. By the 1970s, the British Interplanetary Society designed Daedalus, a fusion starship meant to reach Barnard's star in 50 years. NASA quietly funded studies. DARPA commissioned reports. Private foundations assembled panels of physicists and engineers to ask the same question: what machine could actually cross 4.24 light-years? Each design pushed a different boundary. Each claimed a different trick to beat the distance. Antimatter engines, light sails driven by Earth-based lasers, ramjets that scoop interstellar hydrogen as they fly, fusion torches burning deuterium for decades. The proposals filled journals, conference proceedings, technical memos stamped with security classifications. But one by one, they break. Not because the engineering is hard, but because the universe says no in a different way each time. The first contender is the same engine that carried us off the planet, and it dies first. Chemical chains. Chemical rockets burn hydrogen and oxygen, or kerosene and liquid oxygen, or hydrazine and nitrogen tetroxide. The combustion releases energy stored in molecular bonds. That energy heats exhaust gas, and the gas rushes out the nozzle at a fixed speed determined by the chemistry itself. The Space Shuttle's main engines expelled gas at 4,400 meters per second. The Saturn V's F1 engines hit 2,580 meters per second. No chemical reaction in existence pushes exhaust faster than about 5,000 meters per second, because that's the energy ceiling locked into the atom's electron shells. To reach even 1% the speed of light, you need to hit 3 million meters per second. Chemical rockets give you 0.15% of that. You can't stack engines. You can't run them longer. The exhaust velocity is the absolute cap on how fast you can throw mass backward, which means it caps how fast you can push forward. Every Apollo mission, every Mars probe, every satellite in orbit, all hit the same wall. The Moon is 380,000 kilometers away. Proxima Centauri is 40 million kilometers away. Chemistry doesn't scale across that gap. There is an equation behind this failure, and once you see it, you can't unsee it. The rocket equation. Konstantin Tsiolkovsky published the rocket equation in 1903. It says your final velocity depends on exhaust velocity multiplied by the natural logarithm of your mass ratio. How heavy you start, divided by how heavy you end. To go faster, you either speed up the exhaust or carry more fuel. But the fuel has mass, so you need fuel to accelerate the fuel, which means you need fuel to accelerate the fuel that accelerates the fuel. The mass ratio climbs exponentially. To reach 10% light speed with a chemical rocket, even one that burns perfectly, your fuel would outweigh your payload by a factor of 10 to the power of 26,000. That is more mass than exists in the observable universe. The rocket equation doesn't care about your thrust or your engine efficiency. It is a law of logarithms, and logarithms grow slowly, while exponentials grow fast. Every extra kilometer per second of speed demands exponentially more fuel, and the fuel itself needs fuel. For decades, engineers tried to work around it. Staging helps, but only by a constant factor. In-space refueling helps, but someone has to lift that fuel out of a gravity well first. The equation held. But there was a way to cheat this math, by carrying a bomb instead of a fuel tank. Splitting the atom. A uranium nucleus holds 2 million times more energy than a hydrogen-oxygen bond. That's not an engineering advantage. That's a different universe of possibility. When an atom splits, it doesn't burn, it transforms. Mass becomes energy according to Einstein's equation, and the energy density is so high that a kilogram of uranium-235 releases the same power as 2,700,000 kilograms of chemical fuel. Nuclear reactors had already proven the concept on Earth. Heat water, spin turbines, generate thrust. A fission rocket could theoretically reach exhaust velocities of 20,000 to 100,000 meters per second, 10 times what chemistry allows. But reactors are heavy, and controlled fission releases energy slowly. The engineers needed something faster, something violent. One 1950s project proposed riding the shockwaves of nuclear detonations, and it almost got built. Project Orion. Project Orion was supposed to work like this: eject a nuclear bomb behind the ship, detonate it, catch the blast on a massive steel pusher plate, absorb the shock through hydraulic dampers. Repeat every few seconds. The design wasn't theoretical fantasy. General Atomics ran the program from 1958 to 1965, with serious funding and serious physicists. They built test models, calculated trajectories, solved the engineering of a ship that could survive repeated nuclear explosions at point-blank range. Orion's performance was staggering. A 4,000-ton interplanetary version could reach Mars in 4 weeks. The Interstellar variant, a 400,000-ton beast powered by hydrogen bombs, could theoretically hit 3% to the speed of light. At 5% light speed, Proxima Centauri sits 85 years away. Still a one-way trip, still multiple human lifetimes. The Test Ban Treaty killed the project in 1963, but the math had already delivered the verdict. Even riding nuclear fire, the stars stayed a lifetime too far, so the engineers reached for fusion. The fusion torch. Fusion doesn't split atoms, it crushes them together. Hydrogen nuclei slam into each other under immense pressure and temperature, fusing into helium and releasing energy in the process. It's what keeps the sun burning, and it's 4 times more efficient than fission per unit of fuel mass. A fusion rocket would carry deuterium and helium-3, ignite them in a magnetic bottle, and channel the superheated plasma out the back at exhaust velocities approaching 1 million meters per second. That's 3% the speed of light, purely from the exhaust stream. The specific impulse, the measure of rocket efficiency, would leap from chemicals 450 seconds to fusion's 1 million seconds. The rocket equation's tyranny softens when your fuel carries that much energy. Suddenly, accelerating to 10% or 15% light speed stops being a fantasy and starts being a calculation. Fusion propulsion remained theoretical through the 1960s, waiting for someone to solve controlled fusion on Earth first. But the concept was too tantalizing to ignore. A team of engineers actually drew the whole ship, and its size alone should have been a warning. Daedalus. They called it Daedalus. The British Interplanetary Society spent 5 years designing a fusion starship that could reach Barnard's star in 50 years. The spacecraft massed 54,000 tons, most of it fuel. 2 stages, each burning deuterium and helium-3 in pellet explosions, 250 times per second. The helium-3 alone required strip mining the atmosphere of Jupiter. The ship would fire its engines for 4 years, coast for 46, and never slow down. A one-way flyby, cameras snapping data as the ship screamed past Barnard's star at 12% light speed, transmitting for a few hours before vanishing into the dark. The fuel mass to payload ratio was 400 to 1, and that was already assuming fusion worked perfectly. To do better than Daedalus, you'd need the most concentrated energy in existence, and it fights you at every turn. The antimatter gamble. Antimatter is the universe's perfect fuel. When an electron meets a positron, both vanish. 100% of their mass converts to energy. No waste, no ash. Einstein's E equals mc squared at full efficiency. A single kilogram of antimatter, annihilating with a kilogram of matter, releases 180 petajoules, the energy of 43 megatons of TNT. Chemical rockets waste 99.9% of their fuel's mass as heat and exhaust products. Fusion keeps 0.7% as useful energy. Antimatter keeps it all. The exhaust velocity climbs toward light speed itself. Suddenly, the rocket equation loosens its grip. You could accelerate to relativistic speeds with a fuel fraction Daedalus could only dream of. The catch isn't the physics of the burn, it's that a single mission would need more antimatter than Earth could make in an age. A gram of fury, CERN's antimatter factory, produces 10 nanograms per year. Humanity's total production since we learned how adds up to roughly 20 nanograms. A starship needs kilograms, possibly tons depending on payload and destination. At current rates, making 1 gram would take 100 million years. The production cost alone runs $62.05 trillion per gram, and that's before you solve containment. Antimatter annihilates on contact with normal matter, so you trap it in magnetic bottles, suspended in vacuum, hoping the field never flickers. A power failure, a micrometeorite puncture, a single atom leaking into the trap, and your fuel detonates with the yield of a strategic warhead. You're flying a bomb factory across interstellar space, and if anything goes wrong, the ship doesn't land, it evaporates. So a new school of thought asked a radical question. What if the ship carried no fuel at all? The light sail. The photon carries momentum. Not much. A single particle of light imparts a force measured in femtonewtons. But shine enough of them onto a reflective surface, and the pressure becomes real. A solar sail catches sunlight the way canvas catches wind, accelerating without propellant, driven by radiation itself. Close to the sun, the push is strongest. At Earth's orbit, you get 9 micronewtons per square meter. At Mercury's distance, you get 4 times that, enough to nudge a lightweight craft to velocities chemical rockets can't touch. Icaros flew in 2010, propelled by photons alone, across 20 million kilometers of space. But sunlight fades with distance, dropping by the square of how far you travel. To reach another star, you need a beam that doesn't dilute, a laser array firing from home with petawatts of focused power, tracking a sail across trillions of kilometers. The physics works, the engineering is staggering, and the compromise is absolute. Push hard enough to matter, and the sail can only carry something almost weightless. Breakthrough Starshot. In 2016, Breakthrough Starshot proposed sending not a ship, but a chip, a wafer of silicon, circuits and sensors, total mass under 1 gram, riding a sail 4 meters wide and thinner than a garbage bag. A ground-based laser array in the gigawatt range would fire for minutes, accelerating the probe to 60,000 kilometers per second, 20% of light speed. At that velocity, the journey to Proxima Centauri takes 20 years instead of 6,000. The probe arrives, snaps images, measures magnetic fields and particle flux, then transmits the data back across 4.24 light-years at radio frequencies. By the time the signal reaches Earth, the mission clock reads 44 years, but you've touched another star system within a human lifetime. The engineering is brutal but not fantasy. Adaptive optics to keep the beam coherent through the atmosphere. Metamaterial sails that survive gigawatt intensities without vaporizing. A payload durable enough to endure 60,000 grams of acceleration and decades of cosmic radiation. Every component pushes material science to its edge, but the physics allows it. It might send a camera to the stars, but a person weighs far too much for the beam. so dreamers turned to scooping fuel from space itself. The interstellar ramjet. In 1960, Robert Bussard imagined a ship that never runs out of fuel because it gathers hydrogen from the void as it flies. Interstellar space contains roughly 1 atom per cubic centimeter, mostly hydrogen, drifting in the dark. Deploy a magnetic scoop hundreds of kilometers wide, funnel those atoms into a fusion reactor at the stern, and the exhaust becomes your thrust. The faster you go, the more hydrogen you collect, feeding the engine that accelerates you further. In theory, the ship becomes a self-sustaining system, no fuel tanks, no mass limits, just a runway of raw matter stretching across the galaxy. Bussard's equations suggested you could reach relativistic speeds, coasting on the medium itself. But the scoop that makes it possible also destroys it. Magnetic fields, strong enough to gather hydrogen across that distance, also interact with every charged particle in the flow. The drag from deflecting ions, the energy cost of ionizing neutral atoms, the sheer electromagnetic friction of plowing through a diffuse plasma, all of it resists your motion. By the 1980s, refined calculations showed the ramjet couldn't accelerate past a certain threshold. The very gas it tried to burn had a hidden way of dragging the ship to a halt. The drag trap. The collector itself became the coffin. To scoop ions at relativistic speeds, you need a magnetic funnel tens of thousands of kilometers wide. That funnel interacts with the interstellar medium, creating a drag force that scales with velocity. The faster you go, the harder it pushes back. In 1981, T.A. Heppenheimer ran the numbers and found the crossover point. Below about the speed of light, the ramjet could accelerate. Above that, drag overtook thrust. The engine that promised to drink from an infinite well would choke on its own intake. The dream of fuel-free starflight collapsed into a speed trap built by physics itself. Fission gave us of light speed. Fusion pushed it to 12%. Antimatter offered 30%, if we could ever make it. The light sail reached 20%, riding a beam from home. Each propulsion system hit a different ceiling for a different reason. Every engine has failed for its own reason, but a single, larger obstacle has been hiding behind all of them, and it isn't about engines at all. Generation ships. If speed is forbidden, perhaps time is negotiable. The generation ship abandons the sprint and commits to the crawl. A vessel the size of a city, moving at 1% or the speed of light, carrying thousands. The passengers who board will never see the destination. Neither will their children or their children's children. To Proxima Centauri, at 2% light speed, 215 years. To a habitable world, 50 light-years away, 2,500 years. Entire civilizations could rise and fall inside that hull. The crew becomes a society, then a culture, then a species shaped by the ship. Birth rates managed by algorithm, careers assigned at adolescence, every resource accounted for across centuries. It's a solution only if the vessel can remain a functioning world longer than most nations have existed. If the systems don't fail, if the social contract doesn't fracture, if the descendants 80 generations later still remember why they're traveling. The problem was never the journey's length. It was whether anything human could survive being closed inside it. The closed world. A generation ship is an ecology with no margin for collapse. Water must be recycled at 99.9% efficiency for centuries. Atmosphere scrubbed, crops rotated, genetic diversity managed in a population of maybe 10,000 souls. One failed harvest, one pathogen in the ventilation, one autocratic captain, and the mission ends in the dark between stars. The Stanford torus design from the 1970s proposed a rotating habitat 1.8 kilometers across, holding 10,000 people under artificial gravity. Mass budget, 10 million metric tons. Even at 2% light speed, accelerating that mass requires energy equivalent to the world's total annual output, sustained for years. Then you must decelerate at the far end, or arrive as wreckage. Worse than the engineering is the psychology. Studies of isolated populations, Antarctic winter cruise, submarine deployments, all show the same pattern. Cohesion frays, purpose erodes. The third generation forgets the mission's meaning. By generation 10, the ship is simply the world, the destination a myth, and the systems that keep them alive are maintained by rote, until they aren't. So engineers wondered if the smarter move was not to keep the crew alive, but to switch them off. Sleep among the stars. The solution seemed elegant. Put the crew to sleep, slow their metabolism to a crawl, and let the ship glide through the decades while its passengers dream in the dark. Wake them when the engines fire for deceleration, when the target star fills the sky. No generations, no social collapse, no forgotten missions. Hibernating mammals drop their core temperature to a few degrees above freezing. Their heart rate falls to 5 beats per minute, and they survive winters that would kill them awake. If we could trigger that same state in humans, a 40-year crossing might feel like a single night. You'd close your eyes in orbit of Earth and open them in orbit of another world. The engineering is seductive. Smaller life support systems, less food, less water, fewer psychological barriers. The ship becomes a vault instead of a village. Some studies have induced hypothermia in trauma patients for hours, buying time for surgery, and a few animals can survive being frozen solid and thawed. The leap from there to a multi-decade interstellar sleep looks short on paper. But the body isn't a machine you can simply pause and restart, and the cold has teeth. Frozen travelers. When water freezes, it expands. Ice crystals form inside cells, puncturing membranes, shredding organelles, turning living tissue into a field of microscopic shrapnel. Cryopreservation labs can vitrify small samples, replacing water with antifreeze compounds that solidify into glass instead of ice, but scaling that to a whole human body remains unproven. No mammal larger than a hamster has been frozen, stored, and revived intact. Even if you solve the ice, you face the decay. Cosmic radiation doesn't stop when metabolism does. Over decades, it chips away at DNA, one hit at a time, accumulating damage no repair mechanism is running to fix. You might wake the crew, only to find their cells too broken to divide. Their immune systems collapsed, their neurons misfiring. The sleep that was supposed to protect them becomes the thing that kills them. Tardigrades can survive the vacuum of space in a dehydrated state, and wood frogs freeze solid every winter, but neither wakes up after 50 years. Time is still passing, entropy is still working, and biology has limits chemistry can't erase. The fantasy of the sleeper ship runs into the same wall as the generation ship, just at a different scale. The flesh is the weak point. If we can't ship people, some argued, then perhaps we should ship only the instructions to build them. The seed ship. The seed ship carries no living passengers. Instead, it holds frozen embryos, or digital genomes, or both, alongside the machinery to grow them at the destination. Robotic systems land, construct habitats, and begin gestation in artificial wombs. By the time the first child opens its eyes, the ship that delivered it is already silent. The colonists are born into the world they're meant to inherit, raised by machines or AI tutors, with no memory of Earth except what the databanks hold. It sidesteps every biological trap, no crew to feed, no psychology to manage, no generations to lose the mission. You're not shipping fragile bodies across the void, you're shipping information, the most durable cargo the universe allows. A few kilograms of genetic data and a nuclear battery, wrapped in shielding, drifting for centuries. If it arrives, humanity arrives. If it fails, you've lost hardware, not lives. Some designs go further, skip the biology entirely, and send self-replicating machines, von Neumann probes that land, mine, build copies of themselves, and spread. They could seed the galaxy in a few million years, a blink in cosmic time, turning barren rocks into archives or gardens, or whatever we program them to want. The colonization happens without colonists, the exploration without explorers. It sounds like the clever escape, the way to cheat the cruelty of distance, but strip away the passengers, and one enemy still waits for every craft, an enemy made of time. Time's betrayal. Einstein's equations offer something strange. A traveler moving near light speed doesn't experience the journey the same way the universe does. While decades tick past on Earth, the shipboard clock crawls forward in slow motion. At 90% of light speed, time aboard the craft runs at less than half the rate of a stationary observer. Pushed to 99.5%, and a 10-year voyage in Earth's frame compresses to just 1 year for the crew. They step off the ship having aged a tenth as much as the world they left. The faster you go, the slower your clock runs relative to everything standing still. At 99.99% light speed, the dilation factor reaches 70 to 1. A 4-light-year trip to Proxima Centauri takes 4 years by Earth's measure, but only 3 weeks aboard the ship. The travelers live their brief crossing in what feels like real time, eating meals, reading, sleeping through a single month. Meanwhile, outside the hull, seasons wheel past, governments rise and fall, whole generations are born and buried. It sounds like a shortcut, until you count what you leave behind on the other side of the clock. The relativity toll. Launch a ship toward a star 20 light-years distant at 99.5% light speed. The crew experiences roughly 2 years of travel time thanks to dilation. But back on Earth, 20 years pass waiting for the ship to arrive, and another 20 before any signal returns. The mission planners who approved the launch retire. The engineers who built the craft grow old. By the time the first message comes back, the political landscape that funded the project has dissolved, replaced by priorities no one could have predicted. Push the speed higher, and the gap widens into a chasm. At 99.99% light speed, a round trip to a system 50 light-years away takes the crew about 3 years. Earth waits 100. The travelers return to a planet where everyone they knew is dead, where the language has drifted, where the cities have been rebuilt, and the reasons for going have been forgotten. The faster you travel, the more the homeworld becomes a memory you can never revisit, only a museum you tour as a ghost. To feel what that really means, follow one traveler who comes home to a world that forgot them. The twins return. Imagine identical twins on their 25th birthday. One boards a ship bound for a star 10 light-years away, accelerating to 99.9% light speed. The other stays behind. The traveler experiences 1.4 years outbound, turns around, 1.4 years back. She steps off the ship at age 28, having lived through less than 3 years. Her twin is 45 years old. 2 decades have passed on Earth. The parents they shared are gone. The friends, the career, the apartment, the cultural references, all aged out of recognition. She left a world in one shape and returned to find it reshaped by time she never lived through. This isn't science fiction. It's a direct consequence of special relativity, confirmed in particle accelerators and atomic clocks flown on jets. The equations hold. At relativistic speeds, you pay for your youth with everyone else's age. The twin paradox makes time dilation personal, but it assumes you can reach those speeds and survive the journey. You can't step into a craft, hit 99.9% light speed, and coast. The universe between stars is not empty, and every atom you meet at that velocity arrives like a bullet. And there's a reason no ship will ever cruise that fast without being torn apart. Kilometers per second. To cross 4 light-years to Proxima Centauri in a human lifetime, say 40 years, your ship needs to average 30,000 kilometers per second. That's 10% the speed of light. The fastest object humanity has ever built, the Parker Solar Probe, peaks at 192 kilometers per second. You'd need to go 156 times faster. At 30,000 kilometers per second, you'd cross the distance from Earth to the Moon in 13 seconds. The entire circumference of Earth would pass beneath you in 1.3 seconds. This isn't science fiction propulsion. It's the minimum speed the geometry of interstellar distance forces on you if the crew is going to survive the crossing. And if you want the trip shorter, say 10 years, you need 120,000 kilometers per second, 40% light speed. Every halving of travel time doubles the velocity demand, and velocity is where the physics turns hostile. At those velocities, empty space stops being empty and starts being lethal. The kinetic wall. Kinetic energy scales with the square of velocity. Double your speed and you need 4 times the energy. Triple it, 9 times. To accelerate 1 kilogram to 30,000 kilometers per second requires 450 trillion joules. That's 108 tons of TNT per kilogram of payload. A 1,000-ton starship at that speed carries kinetic energy equal to 108 million tons of TNT. That's 5 times the yield of the largest thermonuclear weapon ever detonated. And you need to supply that energy, then later reverse it to stop. The fuel cost alone makes the ship impossibly heavy, unless you find a way to push without carrying propellant. But the energy ledger isn't the only wall. At 30,000 kilometers per second, every collision becomes a relativistic impact. A stationary grain of sand becomes a projectile slamming into your hull at 10% light speed, and the kinetic energy of that impact converts instantly to heat and shock wave. Even if you found that energy, a single grain of nothing waiting ahead could end everything. A speck of dust. A dust grain 0.1 millimeters across, mass roughly 1 microgram, hits your ship at 30,000 kilometers per second with 450,000 joules of energy. That's the muzzle energy of a high-powered rifle round, concentrated in a point smaller than a pinhead. It vaporizes on contact, flash heating to tens of thousands of degrees and blasting a crater through whatever it meets. Interstellar space contains roughly 1 such grain per cubic kilometer. Crossing 4 light-years, your ship sweeps a column 40 trillion kilometers long. Even with a cross-section of just 10 square meters, you'd encounter 400,000 impacts. Each one punches through metal like paper, unless you carry shielding thick enough to absorb the blast, and that shielding adds mass you can't afford. At higher speeds, it gets worse. 60,000 kilometers per second, 20% light speed, quadruples the kinetic energy per grain. 150,000 kilometers per second, and each speck hits with the force of a hand grenade. No material shield can stop that. You'd need meters of armor, or a magnetic field strong enough to deflect charged particles, or a sacrificial cloud of gas pushed ahead to catch debris before it reaches the hull. And dust is only the solid part of a hazard that fills all the space between the stars. Radiation rising. The hydrogen itself becomes a weapon. Between stars, space holds about 1 atom per cubic centimeter, mostly hydrogen, drifting in near-perfect stillness. But when your ship hits it at 90% light speed, relativity blue shifts every photon and particle into a beam of high-energy radiation. A neutral hydrogen atom, normally harmless, arrives at your hull with the kinetic energy of a fast-moving bullet. The faster you go, the harder it hits. At 99.9% C, the cosmic microwave background itself, remnant glow of the Big Bang, at 2.7 Kelvin, blue shifts into X-rays hot enough to cook electronics and crew alike. Your ship becomes its own particle accelerator, slamming into stationary matter at relativistic speeds, and every collision dumps radiation into the hull. Shielding that worked against dust now faces a steady flux of ionizing energy from every direction, front and side, as the interstellar medium becomes a torrent. Combine the dust, the gas, and the glare, and the void reveals itself as anything but empty. The interstellar medium. What astronomers call the interstellar medium is a thin haze of gas and dust stretching between star systems, averaging 1 atom per cubic centimeter, but clumping into clouds 10 to 100 times denser. In human terms, it's a vacuum better than anything we can make on Earth. To a starship crossing light years at relativistic speed, it's a sandstorm. Every cubic meter you pass through contains roughly 1 million particles. At 0.9 C, you sweep a column of space the width of your ship, colliding with trillions of atoms per second. Each one deposits energy as heat, radiation, or structural damage, and there's no gap in the bombardment. The medium doesn't end, It just thins and thickens as you cross molecular clouds, HII regions, and the bow shocks of stellar winds. You can't dodge it, you can't wait it out. The only way through is to plow straight into a cosmos that resists motion at these speeds with every atom it holds, and the cumulative erosion never stops. Shielding buys time. Magnetic fields deflect charged particles, but both demand power, and power means mass, and mass resists acceleration. Every barrier we've met, speed, dust, radiation, shielding, quietly bills the same account, and it's time to read the ledger. The energy ledger, accelerating a 1,000-ton starship to 0.5 C, requires 1.1 times 1020 joules, the yield of 26,000 megatons, twice the world's entire nuclear arsenal. Shielding, life support, and deceleration at the far end roughly triple that. A round trip to Proxima Centauri, accounting for fuel mass that must itself be accelerated, pushes the figure into the realm of 1021 to 1022 joules. For context, humanity's total annual energy consumption sits near 6 times 1020 joules. A single interstellar mission, one ship, one crew, one destination 4.24 light-years away, demands multiple years of every power plant, wind farm, solar panel, and combustion engine on Earth running at full output and funneling every watt into launch. And that's the optimistic case. It assumes perfect efficiency, no losses to heat or friction, a propulsion system that doesn't exist, and a fuel source dense enough to fit aboard. Real-world engines, even theoretical fusion or antimatter drives, waste 30% to 90% of input energy as heat and exhaust. The true energy budget climbs higher still, into territory reserved for stellar-scale events. The number that comes out isn't a budget, it's a comparison to entire stars. Powering a star, a 10,000-ton ship accelerating to 0.1 C over 5 years, needs roughly 9 times 1022 joules. That's 150 times the total energy humanity consumed in 2023. It's 6 months of the sun's entire output, concentrated into a single vehicle. You could drain every power plant on Earth for a decade and still fall short. You could convert Jupiter's entire mass at 1% efficiency and barely fund a fleet. The energy isn't borrowed from a grid, it's summoned from physics itself, and there's no installment plan. Fusion might deliver 0.7% mass-to-energy conversion. Antimatter reaches 100%, but producing a kilogram costs more energy than exists in all Earth's fossil reserves. The gap between what we generate and what the stars demand isn't an engineering challenge. It's a planetary reclassification. But pouring in that much energy creates a second problem no engine can escape. The waste heat problem. Thermodynamics guarantees that every engine wastes some fraction as heat. A fusion drive at 50% efficiency turns half that stellar energy into radiation that must go somewhere. At 1022 joules, the waste heat alone could vaporize the ship in seconds. Radiators grow with the square of heat load, but mass grows linearly, so the cooling system becomes the ship. At 0.1 C, you're dragging a structure the size of a city just to keep the engine from melting. The faster you want to go, the more waste you generate, and the heavier the radiators become. Even if you improve efficiency to 90%, you're still dumping 1021 joules into space. The ship glows like a small sun, visible across light years, cooking anything within a kilometer of the exhaust plume. Efficiency buys time, but it doesn't eliminate the heat, and the heat scales with ambition. You might imagine a perfect engine erases the problem, but perfection has its own locked ceiling. Fuel you can't carry. To carry fuel for 0.1 C, you need propellant. To carry that propellant, you need more propellant. To shield the fuel tanks from radiation, you need mass, and to accelerate that mass, you need still more fuel. The rocket equation becomes a trap, each improvement feeding back into a heavier ship. A hydrogen-oxygen rocket delivers 4.5 kilometers per second exhaust velocity. To reach 30,000 kilometers per second, you'd need a fuel-to-payload ratio of roughly E squares 6600, a number with 2,800 zeros. 1 gram of payload requires more fuel mass than exists in the observable universe. Fusion raises exhaust velocity to 3% of c. The ratio drops to E cube, manageable until you add shielding, structure, life support, radiators. Even antimatter, with exhaust velocity near c, leaves you hauling fuel mass equal to payload mass for every factor of 2.7 in speed. There's no chemist, no reactor design, no miracle material that breaks the exponential. The equation is written into momentum itself. There is a hard maximum to how efficient any rocket can be, and even the ideal one isn't enough. The efficiency ceiling. So imagine the theoretical ceiling. A propulsion system that converts matter directly into thrust with perfect efficiency. 100% of the mass energy turned into momentum. No waste, no heat. The kind of engine thermodynamics allows on paper, but reality never quite delivers. Even that perfect machine, burning hydrogen into pure directed light, accelerating a crew compartment toward Proxima Centauri, would need a mass ratio somewhere near 10,000 to 1. 10,000 kilograms of fuel for every kilogram of ship that arrives. And that's one way. The return doubles it. The life support, the shielding, the deceleration fuel all get counted in the payload, which means the fuel to move the fuel to move the fuel climbs again. The equation doesn't care how clever the engineering is. You can't trick exponential growth. You can't negotiate with momentum, which forces an uncomfortable admission: no machine we could ever build is the real problem. The deeper barrier, because every failure so far, whether it's the kinetic barrier, the radiation flux, or the fuel mass spiraling into absurdity, those all look like engineering challenges. Build a better shield, find a denser propellant, design a lighter hull. But strip away the technology and you're left with something harder. The equations that govern motion, energy, momentum don't distinguish between a chemical rocket and a photon drive. The limits tighten as velocity climbs regardless of what's burning in the engine. At 10% light speed, the mass ratio breaks feasibility. At 50%, it becomes fantastical. At 90%, the numbers stop meaning anything a spacecraft could physically be. And the curve doesn't level off, it goes vertical, because there's a point where the physics itself says no. Not no as in difficult, no as in the universe has a maximum written into its fabric, and every object with mass runs into it. The wall the whole story has circled turns out to be one number the universe refuses to let anything beat. Causality's edge, 299,792,458 meters per second. The speed of light in vacuum, usually rounded to 300,000 kilometers per second, often written as c. It shows up in every corner of physics, electromagnetism, relativity, quantum mechanics, not as a speed limit for photons but as something deeper. It's the rate at which cause and effect propagate through space-time. When you flip a switch, the electromagnetic field doesn't update everywhere instantly. The change moves outward at c. Gravity works the same way. If the sun vanished, Earth would continue orbiting for 8 minutes and 20 seconds, the time it takes that information to cross 150 million kilometers. Causality, the principle that effects follow causes in a defined sequence, depends on nothing moving faster than light. If something could, you'd have reference frames where the effect precedes the cause. A signal sent, then received before it left. A bullet hitting the target, then fired. Light speed isn't a barrier in the sense of a wall you hit. It's the structure underneath time itself, the scaffolding that keeps past, present, and future in order. Cross that boundary, and you don't just break a rule, you break the order of before and after. The meaning of c, the constant c, 299,792,458 meters per second, isn't the speed light happens to travel. It's the maximum rate at which cause can become effect, the upper limit on how fast information can move from one point in space to another. Light reaches that speed because photons have no mass, nothing to slow them down, so they move at the only speed the universe allows for massless things. When you accelerate a spacecraft, you're adding energy to mass. At low speeds, that energy becomes velocity in a straightforward way. But as you approach c, more and more of that energy goes into something else entirely, the relativistic mass, the resistance of the object to further acceleration. Push harder, and the ship gets heavier in the frame of the outside universe, demanding exponentially more energy for each additional meter per second. At 90% of c, doubling your energy gives you a 5% speed boost. At 99%, doubling it again buys you 0.5%. The curve flattens toward a vertical wall, not because the engines fail, but because space-time itself reshapes the relationship between energy and motion. It's tempting to call it a speed limit we'll eventually beat, and that's the deepest misunderstanding of all. Not a speed limit. Calling c a speed limit suggests it's arbitrary, a rule written by physics that better technology might sidestep. But it's not a rule. It's a conversion factor, the exchange rate between space and time, built into the equations that describe how one dimension trades off against the other. When you move through space faster, you move through time slower, and c is the constant that governs that trade. Einstein's field equations don't include c as a cap on velocity. They include it as the invariant speed, the one measurement every observer agrees on, no matter how fast they're moving. You can't go faster than c for the same reason you can't rotate a square into a circle. The geometry won't allow it. Pouring in more energy doesn't break the limit, it just bends your trajectory deeper into the time dimension, slowing your clock relative to the universe outside. This is why particle accelerators can push protons to 99.999991% of c, but never across the line. The particles aren't hitting a wall, they're running into the structure of reality itself, the fixed relationship between energy, mass, and the rate at which 1 second becomes the next. This limit isn't in front of us on the road, it's built into the road, and into the clock. Woven into time. Space-time isn't space plus time, two separate stages. It's a single four-dimensional fabric where moving through one dimension means moving less through another, and the speed of light is the pivot point, the place where all the trade-offs balance. Travel at c and you move through space at maximum rate, but your passage through time stops entirely. Drop below c and time starts flowing again, faster the slower you go. This is why nothing with mass can reach light speed. To do so would require infinite energy, not because you'd need infinite fuel, but because the equations literally divide by zero at c for anything with rest mass. The universe doesn't round that number. It leaves it undefined, a singularity in the mathematics that reflects a singularity in the structure underneath. You're not blocked by engineering limits, you're blocked by the shape of existence. Every physical law we've tested, from electromagnetism to quantum field theory, is built on this same foundation. The speed of light isn't fast because light is special. Light is fast because it has no mass, so it travels at the only speed space-time permits for anything moving purely through space, with zero movement through time. Massive objects can't do that. The universe forces them to move through time, and that requirement binds them below c forever. Now every thread comes together into the single wall this entire film was named for. The barrier revealed. The barrier isn't one thing. It's three walls built from the universe's deepest rules, stacked so tightly no ship can slip between them. The first wall is causality itself. C isn't a speed you approach. It's the rate time flows when you stop moving through space, and massive objects can never reach it. The faster you go, the more energy you need, rising toward infinity as you near light speed. The second wall is thermodynamics. To reach even 10% of c, a 1,000-ton ship needs 450 million terajoules. At 90% of c, the fuel alone would outweigh every structure humanity has ever built. You can't carry it. You can't gather it. The efficiency ceiling is absolute. The third wall is the void. Radiation at relativistic closing speeds turns every photon into a gamma-ray weapon. The hydrogen between stars becomes a particle beam. There is no shielding thick enough that doesn't make the ship too heavy to move. And the cruelest part is that this wall is not fixed. It's closing in on us as we speak. The universe expands. Space itself is expanding, not the objects in it, but the fabric between them, stretching like a grid, printed on an inflating balloon. A galaxy 10 million light-years away isn't just sitting there. The space separating us from it is growing, carrying the galaxy farther with every passing second. Edwin Hubble discovered this in 1929 by measuring the redshift of distant galaxies. The farther away they were, the faster they receded, not because they were moving through space, but because space itself was pulling them apart. At cosmological distances, that recession can exceed the speed of light, not because the galaxies are breaking relativity, but because there's no limit to how fast space can stretch. A photon leaving Earth today toward a galaxy 15 billion light-years away will never arrive. Not in a trillion years. The space between us expands faster than light can cross it. The photon swims forward through a river flowing backward, and the river is winning. This transforms the barrier. You're not just fighting the energy cost and the radiation, you're racing against a universe that's actively pulling your destination away, adding distance faster than your ship can close it. Expansion alone would be survivable, except that something is pressing the accelerator. The runaway cosmos. In 1998, two teams studying distant supernovae expected to measure the universe's expansion slowing under gravity's pull. Instead, they found the opposite. Galaxies weren't just receding, they were receding faster over time, as if something was overpowering gravity on cosmic scales. The expansion rate 7 billion years ago was slower than today, and the rate today is slower than it will be tomorrow. Every measurement confirms it. The universe is not coasting outward from an ancient explosion. It's accelerating, driven by something woven into the vacuum itself. Adam Rees, Saul Perlmutter, and Brian Schmidt won the 2011 Nobel Prize for this discovery. The Hubble constant, which measures expansion speed, sits around 70 kilometers per second per megaparsec today. That means a galaxy 1 million parsecs, or 3.26 million light-years away, recedes at 70 kilometers per second. At 10 million parsecs, 700 kilometers per second. At some distance, the recession speed crosses c, and no signal from that galaxy will ever reach us again. The boundary is moving inward. Galaxies we can see today will vanish from view as acceleration drags them past that threshold. The night sky we observe now is richer than the one our descendants will inherit. Behind the acceleration sits a force we barely understand, and it is quietly stealing the sky. Dark energy's grip. Roughly 68% of everything in the cosmos is this stuff, and it doesn't clump into stars or planets or gather into clouds. It fills empty space evenly, and it pushes outward instead of pulling in. Ordinary matter thins out as the universe grows, but dark energy holds a steady density, so as space expands, there's simply more of it. That's the strange part. Dilute matter, and gravity weakens. Dilute dark energy, and nothing happens because it doesn't dilute at all. Every new cubic meter of space arrives carrying its own portion of this outward pressure, and the total keeps climbing as the volume climbs. So the balance tips. For billions of years, gravity ran the show, slowing the expansion after the Big Bang. Then, around 5 billion years ago, dark energy took over, and the cosmos began to accelerate. From here, it only tightens its hold. Under its pull, whole galaxies are crossing a line beyond which no ship, however fast, can ever follow. The vanishing galaxies. Picture a galaxy sitting far enough away that the space between us and it is stretching faster than its light can cross. The photons leave, heading straight for us, moving at their full 300,000 kilometers per second, and still they lose ground. The road lengthens beneath them, faster than they can travel it. Those galaxies aren't moving through space to escape us. It's the space itself, swelling in every gap, carrying them off. And once expansion at their distance outruns light, the connection is severed. Not just for a ship, which could never come close, but for any signal, any glimmer, anything at all. The light already in transit still arrives for a while, redshifting, dimming, stretching toward the faintest whisper. But nothing new will ever leave them and reach us again. They slip out of contact one by one, quietly, without a sound. That point has a name and a location, and it marks the true edge of everything we could ever touch. The cosmic horizon. It's called the cosmic event horizon, and it works like the horizon around a black hole, only turned inside out. A black hole traps light trying to leave. This traps everything trying to arrive. Cross it going out, and you can never send word back. In our universe, that boundary sits at about 16 billion light-years. Anything beyond it is already unreachable, not because we lack the engine or the centuries, but because the expanding space in between can never be crossed at any speed physics allows. No warp, no patience, no technology changes that. It's a wall, built into the geometry of space-time itself. And this isn't the comfortable, far-away kind of impossible. It's a hard frontier drawn across the sky right now, sorting the cosmos into what we might one day reach, and what we've already lost. Worse still, that frontier isn't holding steady. The reachable universe is getting smaller every year. The shrinking sphere. Right now, if we launched a ship at 99.9% light speed, we could theoretically reach about 18% of the galaxies in the observable universe before expansion swept them beyond reach. That's roughly 35 billion light-years worth of space, a sphere centered on us, containing trillions of galaxies we might one day touch. But in 150 billion years, that sphere will have shrunk to just our local supercluster. In a trillion years, only the galaxies gravitationally bound to our own group remain accessible. Everything else will have receded past the point where light itself can ever close the gap, no matter when we launch or how fast we go. The reachable universe isn't a fixed volume we're racing to explore. It's a closing door, and we're on the wrong side of the threshold watching it swing shut. Every second that passes, another few hundred galaxies slip permanently beyond the cosmic horizon. Follow that shrinkage far enough, and it leads to a fate of near-total isolation. Islands forever. In the deep future, trillions of years from now, an observer in our galaxy would look out and see only the Andromeda system and a handful of smaller companions. The rest of the universe, the trillions of galaxies that once filled the night sky, will have disappeared beyond an impassable horizon, their light stretched into invisibility. They won't have been destroyed, they'll still exist, still orbit, still burn. But the space between us and them will have grown so fast for so long that no signal, no ship, no method within known physics can ever cross the gap. Each galaxy cluster becomes its own island, adrift in an ocean of expanding void. If a civilization arises in one of those distant islands, we'll never know. If they solve every problem we're wrestling with today, develop technologies we can't imagine, reach heights we'll never see, none of it matters. The universe has already sorted us into separate, unreachable neighborhoods. It means the grandest dream of all, a species spread across the stars, was fenced off before we ever began. The quarantine. The light speed limit binds us to our local patch of space-time. Cosmic expansion erases everything beyond our gravitational neighborhood. Together they form a double lock on the door, a quarantine not imposed by any law or agency, but woven into the structure of reality itself. Every civilization that has ever existed or ever will faces the same walls. No amount of time changes the math. No level of advancement rewrites the equations. You can master fusion, crack antimatter, build ships that coast for millennia, and still the universe expands faster than you can cross it. It's a loneliness encoded at the foundation of things. We're not just separated from distant galaxies by distance or time. We're separated by the geometry of space itself, a barrier that grows stronger the harder you push against it, that turns your own speed into an anchor holding you in place. Yet a handful of physicists refuse to accept the sentence, and they point to a loophole in the fabric itself. The warp escape. The loophole is beautifully simple. If you can't move through space faster than light, then don't. Move space itself. Einstein's equations don't limit how fast space can expand or contract. They only limit how fast you can travel within it. So imagine riding a wave in the fabric, compressing the kilometers ahead of you into meters while stretching the meters behind into kilometers. You're not breaking the light barrier. You're standing still inside a bubble, watching the universe slide past you at whatever speed the bubble moves. Inside, relativity is calm. Outside, the geometry does the running. For decades, this was philosophical speculation, a thought experiment physicists sketched on napkins. One physicist wrote down the actual equations for it, and the result was both thrilling and quietly damning. Alcubierre's bubble. In 1994, Miguel Alcubierre published a metric, a solution to Einstein's field equations that describes a stable warp bubble. The math is clean. Space contracts ahead of the bubble by a factor you choose, expands behind it by the same factor, and the ship inside experiences no acceleration, no time dilation, no tidal forces. You could cross 4 light-years to Proxima Centauri in weeks, subjective and objective time matching perfectly. You could traverse the Milky Way in months. The bubble's speed has no upper limit, because the bubble itself isn't moving through space. It's surfing a coordinated wave of compression and expansion. Alcubierre's paper didn't propose new physics. It used general relativity exactly as written, the same equations that predict black holes and gravitational waves. The geometry was legal. The warp drive, on paper, was real. But the equations only work if you can supply a kind of matter that may not exist at all. The negative cost. To curve space the way the Alcubierre metric demands, you need matter with negative energy density, not antimatter, which has positive energy, not a vacuum, which has zero or slight positive energy. You need something that weighs less than nothing, that pushes space-time outward instead of pulling it inward. Quantum field theory allows tiny, fleeting pockets of negative energy through the Casimir effect, where 2 plates in a vacuum exclude certain wavelengths and create a pressure difference. But the amounts are microscopic, lasting nanoseconds. Alcubierre's bubble, depending on the design, requires the mass-energy equivalent of Jupiter or the observable universe, or more, all of it negative. Refinements have whittled the requirement down to a few solar masses of exotic matter. Still unattainable, still theoretical. No experiment has ever created, isolated or sustained macroscopic negative energy, and most physicists suspect the universe's quantum rules forbid it at scale. The warp drive remains mathematically elegant and physically out of reach, a solution that obeys Einstein's equations but defies the matter we know how to make. If you can't warp the road, some argue, then maybe you can punch a hole straight through it. The wormhole hope. A wormhole is a tunnel through space-time itself, a bridge connecting 2 mouths that might lie billions of light-years apart in ordinary space, but touch back-to-back through a 4th-dimensional shortcut. Einstein and Nathan Rosen discovered the geometry in 1935, a solution to general relativity, where space folds and pinches into a throat. Step through one mouth, and you emerge instantly from the other, bypassing the gulf between. The mathematics are clean. You need a region of extreme curvature at each mouth, mass compressed enough to warp space-time into a funnel, and a throat connecting them. No faster than light travel in the local sense, you're still moving through space at normal speed, but the space you're moving through has been stitched into a shortcut. The problem reveals itself the moment you trace what happens inside. Space-time curvature at the throat pulls inward, gravity trying to seal the tunnel shut. Any disturbance, a passing photon, a gravitational ripple, anything, amplifies the pinch. The trouble is that a natural wormhole would slam shut before a single photon could pass. Holding it open. To hold a wormhole open, you need something pushing outward against the collapse. not ordinary matter. Gravity from mass only makes the pinch worse. You need negative energy density, matter that gravitates repulsively, threading the throat and propping the tunnel open from the inside, like a scaffold holding back a cave-in. Kip Thorne and Michael Morris worked out the numbers in 1988. For a wormhole 1 meter wide, traversable by a human, you'd need the equivalent of the mass energy of Jupiter, but negative, distributed in a thin shell around the throat. Scale the mouth up to fit a spacecraft, and the demand grows to stellar masses, entire suns' worth of anti-gravitating exotic matter. It's the same substance the warp drive requires, but now you need it in concentrations high enough to hold space-time itself from collapsing. The geometry is possible, the equations permit it, but only if you can harvest or create something the universe has never been observed to provide in bulk. So everything now hinges on one question: can the universe actually supply that impossible substance? The exotic dead end. Quantum field theory does allow fleeting violations of the positive energy condition. The Casimir effect, where two metal plates placed nanometers apart in a vacuum experience an attractive force from suppressed quantum fluctuations between them, produces a region of slightly negative energy density. Hawking radiation at a black hole's event horizon involves transient negative energy states. Both are real, measured, and utterly insufficient. The Casimir energy density between plates 10 nanometers apart is roughly minus 0.001 joules per cubic meter. To stabilize a 1 meter wormhole, Thorne's calculation requires densities on the order of minus 1044 joules per cubic meter, a factor of 1047 times stronger. The quantum effects we can observe are whispers. The wormhole demands a scream that drowns out stars. Larry Ford and Thomas Roman proved in the 1990s that quantum inequalities place hard limits on how much negative energy can be concentrated in any finite region for any finite time. The smaller the region and the longer the duration, the tighter the constraint. At the scales and stability a traversable wormhole or warp bubble requires, the universe's own rules forbid it. With the shortcuts sealed off, the last hopes stop trying to move matter and start trying to move only thought. Faster than thought. If a body can't cross the gap, maybe the pattern could. Upload a mind to a laser beam, transmit the blueprint for a machine, send the genome, and let the colony rebuild itself on arrival. Information weighs nothing, needs no fuel, no life support, no decades of shielding against radiation. A digital envoy could ride a photon across the void, while the biological original stays home, safe and aging. It's the oldest science fiction bargain. Trade the flesh for the signal, the ship for the transmission. The galaxy opens if all you need to send is the idea of a person, not the person themselves. Except light still moves at light speed. A radio wave to Proxima Centauri takes 4.2 years. A data stream to a star 10,000 light-years out takes 10,000 years, and the reply, if it comes, takes 10,000 more. The carrier changes, but the limit does not. And in an expanding universe, the galaxies we'd want to reach are receding faster than any signal can chase them. The transmission leaves Earth at 300,000 kilometers per second and still never closes the distance. But a message obeys the same wall as a starship, and the same widening dark swallows it too. The quantum loophole. Quantum mechanics offers one last whisper of hope. Entangle two particles, separate them by light-years, and when you measure one, the other's state changes instantly. No delay, no light-speed crawl, no waiting for the wave to cross. Einstein called it spooky action at a distance, and experiments confirm it happens. So, entangle a billion particles, send half to Alpha Centauri, encode your message in the measurements. Instant communication across the stars, a channel the universe can't throttle. Except you can't control what state the distant particle collapses into. You measure, it responds, but the outcome is random. To see the correlation, both sides have to compare their results afterward, and that comparison has to travel the old way, at light speed or slower. The no communication theorem in quantum mechanics is explicit. Entanglement lets you share randomness instantly, but randomness carries no message. Every other quantum trick follows the same script. Tunneling lets particles slip through barriers but not across cosmological distances. Superposition collapses when you try to read it. The Heisenberg uncertainty trades position for momentum but never gives you both. For every quantum trick that seems to cheat the wall, there's a hidden law that quietly reseals it. The last method, the final proposals grow stranger and more desperate. Beam a seed AI to a distant moon and let it bootstrap a civilization from raw elements. Encode human DNA in synthetic bacteria and scatter them across the galaxy like spores. Build a Dyson sphere, harvest a star's full output, and punch a transmission through spacetime itself with energy no species has ever touched. Each one runs into the same three walls. First, the speed of light. Even information cannot outrun it. Second, the energy cost. Moving or transmitting anything meaningful across galactic distances requires more power than stars produce over centuries. Third, cosmic expansion. The space between us and distant galaxies grows faster than any signal or object can cross it. Warp drives need negative energy. Wormholes need exotic matter. Quantum channels need classical confirmation. Every route that tries to skip the journey ends up blocked by a law deeper than engineering, woven into the structure of space-time and entropy and causality. The universe didn't leave a gap. Even if you accept a one-way trip, even if you're willing to send only data, even if the journey takes 100,000 years, the expanding horizon pulls the destination out of reach before the method matures. The proposals pile up, brilliant and detailed and physically consistent, right until the moment they collide with the limits. With every method exhausted, only one thing remains: to face honestly what living inside this wall actually means. The silence. In 1950, physicist Enrico Fermi asked a question that still echoes: where is everybody? If the galaxy is 13 million years old and contains 400 million stars, why haven't we seen a single signal, a single probe, a single visitor? For 70 years we've called it a paradox, but everything we've walked through suggests it isn't. The energy walls aren't just hard, they're absolute. The time dilation isn't just inconvenient, it's isolating. The negative energy doesn't just fail to exist in useful quantities, it violates the structure holding reality together. If these barriers apply to us, they apply to everyone. A civilization 1,000 light-years away faces the same physics, the same energy scales, the same choice between subluminal crawl and impossible cost. The silence isn't mysterious. It's exactly what you'd expect from a universe that permits local complexity but forbids interstellar contact. We're not alone because no one came. We're alone because no one can. But there's one place the barrier doesn't reach. The radiosphere. On December 16, 1974, the Arecibo telescope beamed a radio message toward the globular cluster M13, 25,000 light-years away. That signal is still traveling, a sphere of electromagnetic radiation expanding at 299,792 kilometers per second, and nothing in the universe can stop it. Every television broadcast since the 1930s, every radar pulse, every navigation beacon has leaked into space. They've formed a bubble roughly 200 light-years across, carrying fragments of human voices, music, data. It will keep expanding for billions of years, long after Earth is gone. An archaeological record written in photons. This is what the universe permits: information at light speed. Not matter, not energy in useful concentrations, not anything that could carry a living mind or a self-replicating machine. But a signal, yes. A message can cross the void, one way, irreversible, arriving millennia after it was sent. We can't go to the stars, but we can speak to them, and they can speak to us, if anyone's listening. Which brings us to the final question: what do we do with the prison we're in? The home we have. The barrier isn't an accident. It's written into the equations that govern time, entropy, and causality itself. If faster-than-light travel were possible, cause and effect would decouple, thermodynamic arrows would reverse. The stable flow of time that lets stars burn and chemistry build complexity would collapse into paradox. The universe didn't lock us in as punishment. It isolated every pocket of order, every spark of complexity, to protect the structure that makes them possible. We're not trapped on Earth. We're anchored here by the same physics that allows atoms to bond, neurons to fire, and civilizations to persist across millennia. Interstellar travel isn't forbidden because the engineering is hard. It's forbidden because the alternative is a universe where nothing coherent can exist at all. The prison is the foundation. The walls are load-bearing. Every intelligent species in the galaxy lives behind the same barrier, a quarantine zone light years across, physically incapable of contaminating or conquering anyone else. We'll never meet. But we're also never at risk of being erased by something we never saw coming. The long view. We walked through chemical rockets, nuclear pulses, fusion torches, antimatter engines, light sails pushed by lasers, ramjets scooping fuel from the void. We examined generation ships, sleeper crews, frozen embryos, digital mines. Every propulsion system humanity has ever conceived runs into the same walls. Energy, time, radiation, dust at relativistic speed, waste heat that boils the ship from within. And beneath it all, deeper than engineering, the universe itself says no. Causality is woven into space-time at the scale of C, and dark energy is already pulling 97% of galaxies beyond any future we could ever reach, even at light speed. The cosmos is expanding faster than physics allows us to chase it. We opened this video reaching for the stars. We close it understanding they were never meant to be reached. But here's what we do have. A single vantage point in space and time from which we can see 13 billion years of cosmic history. Light from galaxies that formed when the universe was young. Radiation from the moment atoms first existed. The view from Earth isn't a consolation prize, it's the gift. If this one felt big, there's a whole catalogue of cosmic-scale questions waiting. Subscribe, and we'll keep walking through them together.